In this video, we're going to take the idea of a vector and just generalize it a little bit more. That's one of the things that linear algebra does so well. It gives you a framework that is easily scalable, extendable, and we're going to do that with the idea of a vector. So you think about what we've done up to this point, the two fundamental operations that are related to a vector space, scalar multiplication and addition. And we have these rows and columns and things like that. But it turns out if you just think about some of the other objects that we've used in previous math classes, or maybe just not even in a formal class, but just for fun, you might realize that there are other objects that can be scaled and summed, and they preserve a lot of the properties that we're used to with these rows and columns. So what we're going to do is just list three of the um, pretty standard ones. In fact, let me go ahead and include our Euclidean vector space, right? So let's start with that. So let's start with Rn. We've seen this before. And then this is how is this defined? So and it's a set. It's a set of all n tuples. So you got x1, x2, dot dot dot, xn. And oh, I didn't put any conditions. So such that like the xi's, for us we've been using real numbers, but you can make your n tuples with whatever entries you want. But the prototypical Rn. Right now, I guess since I said Rn, then yeah, I have to allow for real entries. But yes, and again, we can add them, we can scale them, and we preserve their vector structure. Well, if you think back to the work that we did with matrices, we did a lot of matrix algebra. Well, with matrices, these are things that you can also scale and add and preserve their structure. So for instance, to add them, they have to have the same dimension. To scale them, dimension isn't really an issue because you just basically distribute it. So if you look at the collection of all the matrices of a fixed dimension, just like how the dimension of Rn is fixed, in other words, vectors in R2 are two-dimensional, etc. Right? So here's the notation that we're going to use. It'll be an M, and I want it to kind of look like this little R here. So I'm going to do something like that. So it's going to be an M, and then what defines a matrix now is not just entries, but entries in rows and columns. So this will be our little m and little n. So this will represent, so let me write it out in words. So this represents the set of all m by n matrices. Now, if we wanted to specify, just like how we specified over here, that the entries must be real numbers, if we wanted to limit or specify that the entries in our matrices are real numbers, and we could do something like this. So I'm just going to change my font just a little bit. So we got m sub n by n, and this would be, if I wanted to specify real numbers, I would put parentheses and put our symbol for real numbers there. Oh, just one. I got a little excited there with an extra parentheses. So this would be the set of all matrices, and then we've now said with real entries. Yeah, and it turns out this is also a vector space because, and again, it's not hard to justify that because of all the matrix algebra that we've done, right? So that's one. And then another one that seems a little strange to say at first, but go back to, let's say, your first study of polynomials. And polynomials are things that you can add, right? So if you add two polynomials together, you're going to get another polynomial. If you multiply a polynomial by a constant, you're going to get another polynomial and so forth. So it turns out that if we look at, now here I have to give you a little technical detail. So I'm going to use this P for polynomial, and then I'm going to put a subscript here because polynomials, they have this really key property about their degree, right? So it's the degree that's going to define this. And so this P sub n is going to stand for the set of all polynomials, right? All of them. Notice the word all. That's going to be a theme here. So the set of all polynomials with degree. Now you might be thinking I'm going to say that the degree has to be n. Well, that's not good enough to form a vector space. It's with degree less than or equal to n. So you could say with degree at most, it doesn't look like most at all. So at most, n. Yep. And here's the reason why. And let me just give you an example. You can add two polynomials that are of degree 2, but if their leading coefficients are opposites of each other, then those terms would cancel out, and then you wouldn't have a second degree polynomial anymore. So you have to allow for the possibility that when you add two polynomials, the degree might stay the same or it might go down. It will never go up, right? If you think about the way you add terms, but it could go down. So that's why we have to do at most there. But yeah, so what does this look like? Well, let me say, so I didn't write it out for the matrix one because, you know, we've written down the general matrix, but here's the general vector in Pn, right, or polynomial space, if you will. It will be anything that looks like this. So it's going to be a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and then dot, 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 all the way down. And you could have like a linear term, you know, just a1 times x, and then plus you could have a constant term a sub 0. And then what are the restrictions? Well, the freedom you have, right, and maybe I shouldn't say restrictions, but the freedom you have is that these a's, the a sub i's, can be any real number. So a sub I can be any real number. And when you look at Rn and when you look at Pn, you see a lot of similarities, except look at what happens in terms of the number of entries. So there are, in terms of what you need to form an n-tuple, well, you need n entries, right? But to form a general nth degree polynomial, because you could have a constant term, in other words, a term that does not have a power of x, you actually need n plus 1 coefficients at most, right? Some of these could be 0, which we normally don't write, but if we're writing down something generally in a more abstract way, then we have to allow for that. So that's an important thing to keep in mind, right? So there's that. And then the third one that I want to mention is something actually that plays a huge role in calculus, right? And it has to do with the idea of continuity. So I'm going to use C, so it's going to be C. And it doesn't really, now when you think about like continuity and functions, now if you just think in functions in general, more than just polynomials, one of the important things about a function is its domain. So you could say, for instance, and I'm going to do it this way, you could say, so here's what we do for a notation. I'm going to put in square brackets just for now and explain how we can modify it. So square brackets like this, right? So what is this one? Well, it turns out if you look at the set of all continuous functions on a closed interval, that set of functions, they form a vector space. And here's why. Again, not a formal proof. I'm just explaining where some of these ideas would come from. But if you take two continuous functions and add them, the result will be another continuous function. That's what Calc 1, you know, tells us, right? Some properties of limits and things like that. So yeah, if you add two continuous functions, you'll end with a continuous function. If you take a constant and multiply a continuous function, the result will still be continuous. So it has the closure under addition and scalar multiplication, and we can do those operations. And then it turns out all the other properties as well, the things that we can do with numbers, the things that we can do with matrices, the things that we can do with polynomials, we can extend that to other types of functions. So exponentials, trigonometric, all those functions that have the property of continuity. Is this. So this will be the set of all continuous functions. So let's see, continuous functions on the interval a b. And then of course, just think about this interval here. It can be modified, so for instance, if I say, well, maybe I don't worry, I'm not worried about the endpoints, but maybe it could be an open interval like that, then yeah, you just say all the functions that are continuous on that open interval. It could be the entire real line, again, if you're working with real numbers. So just put that interval there. Just using your interval notation, you can do that. So you can restrict or you can unrestrict as much as you'd like. But the idea of this notion of really extending of what we think a vector is, if you then think of other properties, for instance, that are important to calculus, like, I don't know, differentiability. So there is a way you can denote it. So the c by itself just represents that the functions are continuous. But let's say the functions have to have a continuous first derivative. So not just your f, but your f prime. Then what you do, the way we denote that is we put a little 1 there, right? To say, okay, there's a derivative. And now, so we're looking at all the functions with a continuous first derivative, right? So this would be the set of all, let's just say functions with a continuous first derivative. Because I can give you lots of functions that are continuous on a certain interval, but then the derivative is not continuous on that same interval. But if we restrict it and say, yep, we want the derivative to be continuous as well, continuous derivative on whatever that interval a, b is, then we call that C1. And of course we know there's repeated differentiation, so C2, C3, and so forth, all right? So that I just wanted to plant that seed right now. It's not just the Euclidean things. A lot of people would refer to the Euclidean vector space as like the prototypical finite dimensional vector space, but there are other objects that we work with all the time that have the same algebraic properties of vectors. And just to end this, I want to do a quick example, something related to something that we did recently, but in the context, I'm just going to pick the p space or polynomial space and say this. So this is just a little example and ask this question. So let's say we have, so now I'm going to, just actually, let me not do the subscripts. I'm just going to use f, g, and h, but I'm just going to put the little vector sign there just to say, hey, you know what, we're going to recognize these objects as vectors now. So let's say my f of x is 3x squared plus x minus 1, and then let's look at, let's define g as, let's say, x minus 2, and then let's define h as, let's say, 6x squared minus x plus 3. All right, so yeah, so there are 3, and so these are all polynomials, and I'll just make a note that f, g, and h are in P2. No, I was about to write R2, but P2. Now, what's also true is that these are vectors in P3 and P4, because again, as long as you all of the degrees are less than or equal to your n, then they belong to that space. All right. So here's my question: can H be written as a linear combination of these two? Right? In other words, can I find a scalar such that H of x is equal, or scalars is equal to C1 times f, and then plus C2 times G. Let me ask that question mark. Well, let's see how we would set it up, right? Because, I mean, we've done this with the Euclidean stuff. Let's see if we can do this with our polynomials. We claim that they're vectors. So let me put the 6x squared minus x plus 4 on the left, and I'm just going to set up this this equation and see what happens. So C1 times the quantity 3x squared plus x minus 1 plus C2 times the quantity x minus 2. All right. Well, let's go ahead and actually do our vector operations on the right-hand side. I mean, the left-hand side is already in the standard form, right? You know, for a second-degree polynomial. So not much to do there. But let's distribute the C1. So we will have 3C1x squared plus C1x minus C1. And then let's distribute the C2. And then plus C2x minus 2C2, and then let's collect like terms, right? So let me write this down. So 6x squared minus x plus 4. For like terms, there's only one term that has a x squared on the right, so that would just be 3c1 x squared. Now we have a couple terms that have an x on the right hand side, so it will be c1 plus c2, that quantity times x. And then again, we have a couple constant terms on the right, so that will be different ways you could write it if you want to factor out the negative. And in fact, let me do it this way. I'm just going to write with the plus sign there, and then it'll be plus the quantity negative c1 minus 2c2. All right. So if we want the linear combination on the right, this combination of these two vectors to be equal to the vector on the left, what has to be true is that this coefficient of x squared would have to be equal to this coefficient of x squared. And I'm sure you've seen stuff like this before. And then the coefficient of x on the right would have to be equal to, and we put a little 1 there, negative 1 right there. And whatever that constant term is right here, that would have to be equal to this. And look at this. So even though we're talking about, a more generalized concept of a vector space, we can still take some of these fundamental questions, and what do we get? A linear system. Now this system is really easy to solve. So if we start with the blue, 3c1 is equal to 6. So the only way the blue condition will be satisfied is if c1 is equal to 2. All right, well, let's go ahead and check the green condition. So for the green condition now, c1 is 2, so then 2 plus c2 would have to be negative 1. So the only way this is going to work is if c2 is negative 3, right? And then we have to make sure that we can't just assume that the red condition will be satisfied. So now we're going to do a check and take the negative of c1 and then minus 2 times c2. We got that. And we're asking ourselves, so there's my question mark, is that equal to 4? Let's see. We got negative 2 plus 6, voila. It is 4. So that linear combination does work, right? So it's really interesting that, you can start out with your typical way of thinking about a vector, then you throw some algebra in the mix, and then you kind of reflect on things that you've used in math that follow kind of a similar pattern. You say, well, you know what? Maybe vectors can be extended even beyond what we would typically imagine. All right? So there you go. We have Euclidean, matrix, polynomial, and like functional space when you start talking about continuity and differentiability. But keep that in mind as we move forward, and keep an open mind as far as what is a vector. See you in the next video.